Welcome to The Explainer. Today, we're diving deep into real-time multitasking systems and the brains behind them, the RTOS. We're going to pull back the curtain on the invisible power that makes everything from factory robots to life-saving medical gear work with insane, split-second precision.
Have you ever wondered about that? The secret lies in a very special kind of operating system that isn't just about being fast, it's about being on time every single time. In this world, predictability is king.
So to really get why these systems are so different, let's compare the OS running on your laptop right now with the one inside a high-precision device. You'll see they're playing two completely different ball games.
And this really gets to the heart of it. A standard OS, like the one on your computer, its main goal is fairness. It juggles everything so you can browse the web, play music, and have a chat open all at once. But a real-time operating system, or RTOS, well, it's more like a strict drill sergeant, obsessed with one thing and one thing only, hitting its deadlines, period.
These systems really come in two main flavors. You've got hard real-time, where missing a deadline is a total, catastrophic failure. Think about an airbag deploying even a fraction of a second too late. No good. Then you've got soft real-time, where a little lag, like your video stream buffering for a second, is annoying for sure, but it's not going to cause a disaster.
So, what's the secret sauce? How does an RTOS actually pull off this incredible feat of timing? Well, it all comes down to how it thinks, in terms of tasks, priorities, and a lightning-fast process called context switching.
Okay, so first step, every single job the system needs to do is broken down into a task. You can think of it as just an independent function, and the RTOS is constantly keeping tabs on these tasks, tracking whether they're ready to go, actively running, or maybe blocked, just waiting for something to happen.
Now, this is where it gets really cool. Each task that's a priority level, and this is absolutely crucial. A high-priority task, like controlling a motor, has the power to interrupt, or what we call preempt, a lower-priority task, like sending some data to the cloud. It basically says, hey, I'm more important, get out of the way. This makes sure the most critical job gets the CPU's full attention, right now.
So how does it do all this swapping around without dropping the ball? Well, the magic behind that constant juggling is a process called context switching. It's how the RTOS can flip between tasks thousands of times a second without ever losing its place.
Okay, so let's walk through it. Picture this. An interrupt happens. Maybe a critical sensor has new data. The RTOS immediately saves the exact progress of whatever it was doing, think of it like putting a digital bookmark in a book, into something called a task control block. Then the scheduler instantly picks the new, more important job, loads its digital bookmark, and lets it run. To that new task, it feels like it was never even interrupted. It's seamless.
All right, so you've got all these tasks buzzing around at the same time. How do you make sure they cooperate and don't, step on each other's toes or mess up shared data? Well, that's where a clever set of synchronization tools comes into play.
First on our list is something called a mutex, which is just short for mutual exclusion. Its whole job is to act like a guard for a shared resource, like a bit of memory or communication channel, to prevent a nasty problem called a race condition.
The best way to think about it is like a key to a single-person bathroom. Only one task can hold the key and be in the room at a time. If another task comes along and wants to use that resource, it has to wait in line until the first one is done and hands back the key. Simple, but it guarantees exclusive, safe access.
Next up, we've got semaphores. Now, if a mutex is all about locking a resource, a semaphore is all about signaling. It's like sending up a flare to say, hey, something happened.
So imagine you have a task that's just sitting there waiting for a new sensor reading. It can basically go to sleep. Then, when an interrupt comes in with that new data, it raises a semaphore flag. And that instantly wakes up the sleeping task and tells it, hey, the data you were waiting for is here. Time to get to work.
And finally, what if tasks need to pass actual data back and forth, not just signals? For that, they use a queue. Think of it like a super secure, perfectly ordered mail inbox. One task, say a SensorTask, can drop off messages, the data readings, into the box. And then another task, maybe one that handles communications, can come along later and pick them up, one by one in the exact order they were sent. It's a really clean way to pass information without the tasks ever having to interact directly.
Okay, so all this theory is fantastic, but at the end of the day, real-time performance is only as good as the hardware it's running on. So let's look at 3 really popular platforms and see how they stack up for these kinds of demanding jobs.
And just look at the difference here. The timing precision, what we call interrupt latency, is just staggering.
An STM32 can react to something in as little as 1 microsecond. A Raspberry Pi, on the other hand, running a full Linux operating system, can take 50, even 100 times longer. In the world of real-time, that's an eternity.
So the STM32, this is your specialist. This is the Formula One car of microcontrollers. It's built from the ground up for one thing: deterministic, hard real-time performance. It's the go-to choice for those mission-critical jobs like industrial control or high-precision robotics, where every single microsecond literally counts.
Then you've got the ESP32, which is the super versatile all-arounder. Its secret weapon? It's dual core. And that is fantastic, because you can dedicate one core to do your super time-sensitive control stuff, while the other core handles all the messy, complicated things like Wi-Fi and Bluetooth. It's the perfect balance for most modern IoT devices.
And finally, the Raspberry Pi. It's an absolute powerhouse, no doubt about it. But because it's running a full-blown general-purpose Linux OS, it's really playing a different game. It's best suited for soft real-time. It can't give you that microsecond guarantee, but it is a beast at juggling complex things like processing images, streaming video, and logging tons of data all at once.
So, after all that, what are the big things to remember? Let's boil it all down to the key takeaways from this explainer.
It really all comes down to picking the right tool for the job. If you need ironclad, hard, real-time guarantees, you need a specialist, like the STM32. If you need connectivity mixed with good timing, the ESP32 is your sweet spot. And for complex, high-level multitasking, the Raspberry Pi is king. But if there's one thing you remember, make it this: an RTOS isn't about being fast, it's about being predictable. And that predictability is all managed by those essential tools: mutexes, semaphores, and queues that keep the chaos organized.
And that leaves us with a final thought to chew on. As our world gets more and more automated, with AI and robotics weaving into everything from self-driving cars to our home assistants, where is this need for microsecond precision going to matter most next? What's the next everyday object that's going to need these hard real-time guarantees to keep us safe? Thanks for joining this explainer.